So what we're going to do today is pretty much the same thing, except this is as far as we're going to go. And after today, we're going to be able to look at two structures. See, they're pretty much the same molecule, but there's two ways of drawing the Lewis dot structure. Everything has octets, number of electrons is right, but one of these is a lot better than the other one. This one is a heck of a lot better. It's the real answer. It's the lowest energy form of that molecule. That means that's what exists in nature, and that's it. That's the answer. Well, how do you know? Formal charge. Formal charge. That's how we're going to figure out which one's the best. Okay? Now, if we're going to use this formal charge, let's go ahead and take a look at it. Let's jump right into it. There's the structure for phosphoric acid. So let's just do things how we usually do them and get our Lewis dot structure. So April, what would you do first? Find the what? The number of valence electrons. She's even using the right words. Valence electrons. So I've got 3 hydrogens. Phosphorus, which is how many? Everybody, it's got 5. And 6 oxygen. Or no, 4 oxygens. Each one has 6. 4 times 6. And that's everything, right? So that's 8 and 24. Should be 32. Okay. How I like to do stuff, I just like to get there as quick as possible. So I'm going to make octets, connect everything, make octets on everything. Anything left over, put on the center atom. But first, let's figure out how many I used up. Right? If I have any left over, I'll put them on the P. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Used all 32. So the whole point of what we've done over the past day or so is to get to this point. So we can follow the octet rule, we can follow CNOS, all that's to get the best answer to the quickest way possible. But this isn't the best answer, but we drew this structure really quick, just following the octet rule. And what we're finding out today is it's not enough. But we got here. We're so close. So now we just have to test formal charges. And what is this stuff? Well, is it the best structure? Let's find out. We're going to calculate a formal charge. We're going to calculate a formal charge for every single atom in that molecule. You have to do it, for each H, there's 3 times. For each oxygen, there's 4 more times. And then for the final answer for the P. You have to go through this equation. Get the formal charge of every atom. Find its valence, minus number of bonds, minus number of electrons. Okay, no big deal. Here's some helpful suggestions here. What we're going to do is we're going to choose a Lewis structure with all formal charges as close to 0 as possible. So if you get all zeros and everything, that is your answer. You can't get it any better. The sum of all the formal charges equals a charge. So if you had something like, carbonate, you add up all those formal charges, the 3 oxygen formal charges, the carbons, you add them up, you're going to get a negative 2. Can you get all zeros then? You can't. You're going to get negative 2 is going to be your total. So all zeros is not going to be your best answer all the time. Not when there's a charge. When there is a charge, make sure that the negative number, that negative formal charges are on the most electronegative atom. How do you look at a structure and know what the most electronegative atom is? Caroline, what was the trick to figuring out electronegative atoms? The most electronegative atom on the planet is fluorine. So as closer you are to F, the more electronegative you are. That was the trick. So if you ever have F in a molecule and you need to have a -1 formal charge, it's going to be on that F. Okay. So those are the suggestions. Let's go ahead and see if we can get this to work. So let's use formal charges as a guide to determine the best structure. So let's just work up here since we have it. All right, it's a lot easier. Clean this up a little bit. Okay. So summer, let's try this top oxygen right there. He's going to equal that his number of valence is what, Summer? 6. Minus the number of bonds, Kelly. How many bonds with that O? There's just one bond to him. Minus 1. And then minus the number of lone electrons, Eric. He's the dots. He's the dots. It's going to be 6. The lone electrons, 6. There's 6 dots. So already we're kind of messed up because there's no charge on this thing. It's H3PO4. There's no charge. Best answer is all zeros. And we already got a -1 here, so you know something's wrong. Okay. Let's try this H. Monica, the number of valence on hydrogen is, Monica Lopez. 1. Minus Jesus, the number of bonds with that H. 1. Minus the number of lone electrons, Alyssa. 0. Hey, we got a 0 finally. Good deal. Now all those H's are the same, so let's just put zeros by all of them. Right? They're all exactly the same. Monica Soto Ruiz. Let's check out this oxygen. Notice he's the same as the other 3, so we just need to do this once. Number of valence, Monica, on oxygen? 6. Paul. Bonds? 2. Priscilla. Lone electrons? 4. Hey, we got 0 again. So all those guys are zeros. April, this molecule doesn't have any charge. Best answer is all zeros. So, we haven't done P yet. Let's do P. The P. Jared, number of valence? You want to help him? 5. Number of bonds, everybody? 4. Number of lone electrons? 0. He's got a +1. He's got a +1. Well, yeah, they do. You add up all the formal charges, you have to get the overall charge. So you get 0. But there's room for improvement because this thing says get all the formal charges as close to 0 as possible. So if you can't get them to 0, well then fine, you're done. But you can try. So the only choice is to make a double bond. And notice the guys who are 0, don't mess with them. Otherwise you're just going to screw them up. Right? So let's leave them alone. Let's make a double bond. Let's go back to what we had, though, first. Recopy it. We've got a P, an O, an H, an O, an H. Otherwise it's going to be hard to see what to do here. And an O. And just make it what we had. Okay, let's go back to what we had. And remember when you're doing this, before you make a double bond, erase first. Otherwise you can screw up your total here. So I'm going to erase those 2 and make a double bond. So the only ones I messed with is that oxygen and that P. Yeah, it was that CNOS thing, right? Now, yeah. And you have the octet. How I think the book is trying to get us to do this is they're trying to get us to the best answer as fast as possible. So if you follow the octet rule and you follow CNOS, 90% of the time you've got the best possible answer. But you still have to do formal charge to check it. But if you do CNOS and the octet rule, it gets you really, really close. And then you do formal charge just to make some minor modifications, if you have to. So that's kind of, I think, why they had you do CNOS. But yeah, because it definitely doesn't fit. But let's see if we can get all zeros. Then it actually works. So phosphorus, number of valence, Caroline, is 5. Minus the number of bonds, everybody. 5. Lone electrons? 0. So he's 0. He works. How about that oxygen? Number of valence is 6. Minus number of bonds. 2 minus number of lone electrons. 4. He works. This is how it exists in nature. That's your best answer. Okay? It's all zeros. So that's kind of where we're headed. One more thing before we go to the boards and have some fun here. We're going to calculate enthalpy of a reaction using a table, though. April, what was another word for enthalpy? Started with an H. Heat. Some reactions give off heat. Some reactions absorb heat. Just find the amount of heat involved in a reaction. Here's another way to do it besides how we did it in the past. What we're going to do is we're going to, well, think of it this way. For this reaction to happen, imagine these are all the reactants, right? Break all these bonds. Then on the product side, don't break them, but put them back together, form them, right? So that's really all we're going to do. We're going to see how much energy it takes to break all these bonds, see how much energy is given off when you form all these bonds. You pretty much use that to get delta H. It's right up here. We're going to add up all the energies of the bonds that were broken, subtract out the energies of the bonds that were formed. So the minus sign takes into account, energy being given off, so we'll be okay. And you can, do you see how some of these H's don't even, right? Like these bonds, they don't even break, right? They're still there. So you can look through this and try to reduce the math a little bit and not worry about those bonds. But I don't like to do it that way. I like to just break everything and form everything, and then you don't have to worry about, oh, he didn't change. It just seems a lot faster. You have calculators, so why not? Right? So let's try this. My delta H for the reaction. I'm following this equation here. The sum of all the bond energies broken. Okay. So I want to break those CH bonds, Kelly. In fact, I want to break 1, 2, 3. I want to break 4 of them. 4 times what energy, according to that table? You see it? 432? Well, 432 would correspond to HH. 411, right? Can you see 411 in the table? That's what it's got to be. 4 times 411 plus, let's break that C double bond C, Eric. How much energy for that one?
346.
Oh, that's single.
Yeah, double bond C would be 602, right?
Yeah, double bond would be 602. Okay. Is there anything else I have to bust up? Yeah, the H2. Now, I wish they would have wrote it. They didn't, though. Would have made more sense if they would have wrote it that way. But they didn't. That's fine. So what bond do I have to break there, Monica Lopez? How much energy? Yeah, the 432. It's the HH. All right. Minus, okay, now all the ones I'm going to form. 1, 2, 3, 4, 5, 6 of those CH bonds. And we said they were 411. Yeah, thank you. 6 of those. And we also have to form a CC, Jesus, which is how much? 346. Okay, see what we get here. 4 times 411 plus 602 plus 432. And then subtract out all this stuff. 6 times 411. Okay. Anybody get an answer? I got negative 134. I don't know if that's right. Did you? Oh, great. Okay. Negative 134. So, Alyssa, you don't want to lose points, though, for no units. Yeah, she was looking at the table when she saw it. Just look at the table. Kilojoules per mole. Yeah. Okay. It's not so bad. So there's two types of problems. One is finding delta H for a reaction. Add up all the energies for everything to break. Subtract out the energies for everything to form. It's not so bad. Use the table. Okay. The other one is writing Lewis structures, but using formal charges. So to get a formal charge, number of valence minus the number of bonds minus the number of lone electrons. You could also do number of valence minus number of electrons minus number of bonds, right? It doesn't matter. The order really doesn't matter. So let's go to the boards and see if we can knock these out, and then we'll call it a day. I changed the order. I want to do this fluorine compound first. So we can help each other out. So let's draw the best Lewis structure we can. Notice that there's no charge on it. So your best answer, if you can get it, is all zeros for formal charges. Give it a shot. Get the number of valence. Try to make octets. Do your best. And once you did your best, do formal charges to see if you can improve your answer. So what are you getting as a total? 26? I see a lot of 26s. So hopefully you're working with 26 electrons. Now you can go a little bit further because you want to make octets. Oh no, he does that in an octet, doesn't he? Yeah, you're done. So try the, see if it works. Whoop, I'm sorry. I scribble this down. So a lot of folks just following the octet rule and that sort of thing, and then CNOS, this is where they're at. And see if you can improve on that Lewis dot structure. Number of valence minus the number of bonds minus the number of lone electrons. That's how you get formal charges. The fluorines are good, so don't mess with them. So you got to mess with these two guys, right? Well, the fluorine. Fluorine. Oh, Paul, there's where you messed up. Fluorine has 7 valence. That should be a 7. So 7 minus 1 minus 6. You get 0. So the fluorines are looking good, right? You should be getting zeros for them. So that it's the sulfur and the oxygen that are messed up, right? You get a 1 and a negative 1. So you can fix it. So the question is, which lone pair do you erase? You might want to have someone around you, right? Erase the lone pair on the S and make a double bond. Another person erase the lone pair on the O and make a double bond. One of those has to be right. Which one is right? Okay, erase one on the O. I see a lot of, yeah. Erase one on the O, they're saying, to get the best answer. Erase a lone pair on the O. Now everything turns out to be zeros. All right. If you erase a lone pair on the O, you get all zeros. Good. If you got it, try the next one if you got it. Bromate, BrO3 with a minus. Now, before you start with bromate, can you get all zeros? Is that a possibility? Because all zeros is usually the best answer, right? But bromate has a negative charge. So that means a negative, one of these elements has to have a negative formal charge. Would you want it to be the bromine or the oxygen when you finally get this best answer here? The oxygen is closer to the F. So use that as kind of a guide. You want your formal charge, your negative one, to be on the oxygen. That's going to give you the best, most natural answer, because it's more electronegative than bromine. What are you getting as your total for bromate? What are you guys using as your total? Oh, excuse me. 26, right? You have to add 1 for that negative charge. So hopefully you're using 26 electrons for your bromate. So we see if we can make it better. What happens if you make one of these a double bond? What happens to its formal charge?
Doesn't become 0.
Okay.
But I still have negative 1 there.
So make him a double bond too then, maybe. I don't know. Yeah, but you want one of these guys to be a negative.
Okay, yeah.
So what is he going to be?
0. Because it's 1, 2, 3, 4, 5.
There you go. Yeah. You got it. Show people what you did. Okay. So he's a 0. That looks good. But now he's a negative 1. He's a negative 1. And then he's a positive 2. So see if you can improve it.
I think it's positive 1.
Look at this guy. This is 0, 0, negative 1, and this is 0, right? Yeah. That's see how the numbers are all zeros, except you have a negative 1, and he's on the oxygen.
Okay.
So your best combination for formal charges, and looking at this bromate, is zeros for everything, with a single negative 1, and that negative 1 is on a oxygen, right? And some folks have figured it out. They put let me see, Jesus, what'd you do? You have a double bonds. So that gave these oxygens to be zeros, right? And then here's my negative 1. All right, so he's 0. He's 0. He's negative 1, and that bromine is 0. Okay? This one is a job. I moved this one to C because this one takes some work to figure out. But make sure you can get bromate first. Make sure it makes sense to you. Paul, does it make sense? You see how we got it? Okay. So here we're right here. So you have a negative 1, negative 1, negative 1. This guy is
Positive 1.
7. Well, that's right. 7 minus 3 minus 2. That's going to be positive 2, right? Because right. Okay. So positive 2. So it works because negative 1 is negative 2, positive 2 is 0, and negative 1. So they all have to add up to be the charge. So this works, except can you get it better? The best answer is zeros on everything with a negative 1 on only one element, and put it on one of these oxygens because he's more electronegative than the bromine. So yeah, but when you do that, make sure you erase first. Erase first. Okay? And then do it again. Yeah, do it again. There you go. Okay, now he's 0. He's 0. He's still negative 1. If you do the math on him, he's not 2 anymore. He's going to be 7 minus 1, 2, 3, 4, 5 minus 2. He's 0 now. So this is the best answer. So these aren't negative 1s anymore. These are zeros. You can figure out NCLO. You're doing pretty dang good. This is a hard one. At least I struggled with it. Oh, it's just Priscilla, it's just NCLO. There's only one O. Oh, that other O is for the bottom question. Sorry, that if you're reading this, that other O is for the bottom question. It's just a straight nitrogen, chlorine, oxygen. Linear molecule. Did you get all zeros for everything?
What does it say about the sun?
Well, there's no charge on it. So that means the best possible answer is all zeros. And if you can't get all zeros, then you got to stay with it. But you can get all zeros on this thing. So you just got to keep going. Yeah, all the charges will add up to be 0. If they don't, if all the formal charges don't add up to be the overall charge, you screwed up somewhere. Should be working with 18 electrons. How's it going, Caroline? Oh, you got 0 on something. On this one?
Yeah.
Don't mess with him. Leave him alone then.
Okay.
Okay. How about this guy? What is he?
I can't figure these out.
7. So this is 7 minus 3 minus 2. He's going to be a positive 2. All right, so let's try this one. Put him over there. Now what happens?
It's going to be 5 minus 2 minus 5.
Yeah. He still doesn't work. All right. Did you get it?
She triple bonded it.
Oh, she got triple and it works, huh?
So if I triple bond.
Did you get it too? Yeah, people are finding this triple bond thing is working, isn't it? All right? Alyssa, don't need to erase it yet. I need to write it down what you got. Oh, I can see it from over here. All right, did you get it to work? Yeah. Yeah, folks are finding a triple bond works. All right, let me copy somebody's. I get all zeros. That's a hard one. That is a hard one. Try, if you got it, try D. It's another linear molecule. This one's hard. But if they did the, yeah. You get 0 on this one? 7? Maybe you have too many dots. Yeah, you have too many electrons in here. Somehow you lost, you made a bond without erasing. So now if you take 7 minus 1, 2, 3, 4, 5 minus 2, yeah, then you get 0. Hey, this one works?
Yeah, it actually worked.
That's a lot easier than this whole triple bond thing, isn't it?
Yeah.
6 minus 2, 4, 6, 8, 10, 12, 14, 16, 18. Yeah. 7 minus 3
You
minus
can also do the
1.
triple bond also.
Yeah, but this answer looks nicer. I'm going to copy down Paul's answer. There's another possible answer. I'm going to copy down Paul's. NCLO. And then you got a chlorine. So this is kind of a nice answer too. So Paul got a nice answer for that C too. He just has a double bond on the chlorine oxygen. Okay, so that's another possibility. Got all zeros. Use the right number of electrons. 620. Yeah. Looks good. So HOCLO should have 20. Oh, sorry, Eric. There's another oxygen up here. It's hard to see it. You see? There's another O up there. So you got HOCLO to work? Oh, no, I mean, Carolyn, you got this one to work?
Which one? Yes.
This one? Okay, good. Okay, good. Glad that you got it. Huh. Seems to work, right? That's what Alyssa got too. Do HOCLO. I'm copying yours, Monica. Oh my goodness, thank you. And then there's one more. Copy yours, Eric, here. You got all zeros. Good deal. You got it. Couple minutes left. So soccer's all over, right? You guys won everything?
It's not the national championship.
Yeah?
We didn't win that, so
Oh, but you made it to the national championship. What was the score in the end there? Oh, really? Oh, jeez. Dang, that's close. Oh, now you can put all your time into general chemistry. All right, have a good day.